that what you guys got?
Can we view it as
Zoom it, I'm sorry.
Because it's 1 over 12, right?
Exactly. 1 over 12. So the second one was 66.7 parsecs. Right?
Can we go to slide view? It would look bigger. I'm just.
Yeah, sorry, it's a silly program that I use. Right?
Oh, it's PDF. Okay.
Yeah, so here, right, you have to divide by 2. That was the point that, is that clear to you guys?
Oh, because they're giving you theta.
Yeah, because they've given you theta.
Now, if you look at the astronomy CD, there is a manual, okay? Zahid is saying, Jabran is saying these examples come from that manual.
Yeah. Sometimes I use the manual examples if they're good. Oftentimes I find they're not very good, so I'll write my own in those cases. So in this case I use the manual because these questions, parallax is a very straightforward thing.
So if you look on your astronomy CD, there's like a 200-page PDF file, and that's this manual.
Yeah. And then for the last one, if you just look at the equation, it's clear, right, that it's a linear equation. So if you double the baseline, right, you're going to double the angle that you view for something that's at the same distance. So I think from that you can easily just say that the ratios of the two is 1 to 1.5, right? The bigger planet has 1.5 times larger angle, right? And from that, straightforward, because it's a linear equation, you can say it's 1.5 times farther. That's how I would do it, but there's other ways to do it. I don't think you really need to go through this. Here's the algebra for setting up that ratio. And these are very simple equations. You just got to work with them. You'll get used to it. So I suggest if this isn't clear to you, just work out a few more problems on your own.
So both these planets are planets going around our own sun. So they are all extremely far from that other star.
But parallax is simple because it's just this geometry, right? If worst case scenario you forget the equation, you should be able to easily derive it just from if you know trigonometry. But you should just memorize it rather than derive it. Okay, so let's move on to. I wanted to put a break here, but we're not going to since we already had one. Unless you guys want a break, or should we keep going? Do you guys need a break?
I think we can keep going for a while. I'll tell you when they need a break.
Okay. So now today we're going to start talking about the electromagnetic spectrum. This is a very crucial thing to realize, is that what we see as visible light is a very narrow range within the much larger electromagnetic spectrum. So visible light is here in the electromagnetic spectrum. And why it's called electromagnetic is because the phenomena of light waves are comprised of electric and magnetic fields. It's beyond what we're trying to do here to go into the details of how that happens, but that's why it's called electromagnetic. Light is an electromagnetic phenomenon. It has electricity and magnetism as its root causes. Visible light, the light we see in this room, the light we see, the colors we see, are a very narrow part of this electromagnetic spectrum. Have you guys covered this yet, or are you guys covering this now in your physics courses for the juniors? You guys learn it in chemistry. So, Evan, have you seen this?
Yeah.
Okay, so then I don't need to go into too much details, but just to say that it's a broad range of so what defines, I guess I should say, an electromagnetic wave is its wavelength or its frequency. You guys all know what waves are, right? Like this. The wavelength is this distance, right? The distance between peak to peak. And we always call that lambda, right? And frequency is how long it takes from one peak to the next peak, the time. And we usually use nu for that. Here I've used f, but you can use f too. But nu is generally the one you use. And there's a very simple relation for light. The wavelength times the frequency equals the speed of light. In actually any transverse wave, this relation usually holds. And so this equation you need to know. This gives you the way to convert between wavelength and frequency. And oftentimes, so astronomical phenomena occur across this whole range. And when we start looking at these DS9 images and these different objects in the sky, we're going to be looking at them in different electromagnetic bands, right? So, for example, we might see something in the visible. It's an optical image. They took a telescope and took a picture. But then sometimes we might look in the ultraviolet, right? And so you have to be clear that when you're looking at these images, they're false color. That's not actually the real color of the image, right? That color has just been applied because we cannot see UV radiation. So we make instruments that can detect UV radiation, and then we make a picture out of it in visible light that we can't see. So whenever we start looking at these objects, it's crucial to keep in mind that that's not what it actually looks like. Those colors are false colors because we have no way of being able to represent it other than in visible light. And then we might look at, for example, radio waves, right? And look at radio wave phenomena. And it's, I think, worth knowing the bands and what their energy, what energies correspond to what bands. So the most energetic phenomena is gamma rays and X-rays. And then after that comes the ultraviolet. And then there's a small band of the visible that we actually can see with our eyes. And then there's infrared. We can't see infrared, but infrared is like, for example, me and you are radiating it in the infrared. And I'm sure you guys have seen like, Predator or like a cop show where you see like the heat signature, right? The infrared goggles or something. That's because our temperatures of our body are radiating at this frequencies in the infrared. Then it's microwaves and radio waves. So that's generally speaking, the most energetic phenomena are going to be associated with the most energetic particles. So really highly energetic phenomena will have X-rays and ultraviolet, and so on and so forth. Although most objects emit over all frequencies. So you can learn a lot from looking at the different frequencies. I mean, astronomy for about 400 years was just limited to this visible light, right? All we could do is make telescopes like the way Galileo did and just point them at the stars. But then in the 1950s, people started realizing you can also use radio waves to study stars, right? Because we had radio detectors. That's how a radio works. A radio takes a radio wave out of the sky and basically you tune your radio to that particular frequency, and then you can hear a signal. We had the technology, and in about the 40s and 50s, they pointed it at the stars and started learning about the universe through that new window, the window that was opened up by radio waves. The phenomena that you can see with radio waves, you cannot see in the visible. So all of these are complementary. And it's crucial to be able to really understand something. You need to have what's called multi-wavelength coverage. And the images we're going to be looking at are going to have that. And then so the only other equation you really need to know is that the energy of the radio wave is this constant h, which is Planck's constant, times its frequency. Or conversely, because of this relation up here, lambda times the wavelength times the frequency equals c, hc divided by the wavelength. Okay? So this one is one of those things you need to have written down. H,
6.6 times 10
okay, thank you very much. It's a very small number. The 10 to the minus 34. 34 is extremely small. So one individual light wave has very little energy, unless it's extremely high frequency, like an X-ray. So the thing is, though, in this room, there's billions upon billions and trillions of light waves, photons, individual particles of light. And so when you have a lot of them, then you can get really energetic phenomena. So to begin with, we're going to start with what's called black body radiation. So what a black body is, it's an idealized physical object. Imagine the way people usually describe it is it's an object that absorbs light without reflecting any of the light off of it. That's why it's called black. And in physics, there's Kirchhoff's law says that if something absorbs light really well, it also emits light really well. And so it's the best possible emitter of thermal radiation as well. The reason we talk about this is a very idealized case, but it gives us so much information about physical phenomena. It's remarkable. So the radiation itself is thermal kinetic energy converted into electromagnetic radiation. So I assume you guys have started talking about in your physics class, or probably in chemistry, you must have talked about what temperature is, right? So why is something hotter than something else? Right, exactly. The individual particles, right? The temperature in this room. The reason it feels hot outside is the particles are moving faster outside because the temperature is higher. When those particles hit your arm, they leave a little bit of energy because they bounce off of your arm. The higher the temperature, the faster they move, the more